Okay, I'm going to go through the rest of this paper. I did part one with the multiple choice questions and some of the mechanics questions. I'm now going to go through the remainder of the questions which I didn't do. I use this as a practice exam for Edexcel linear because linear, although Unit 1 international A-level students have already taken this module. So Unit 1 took this exam on Friday. It's also excellent practice for linear Edexcel because linear Edexcel is on Wednesday coming up, and the paper 1 of linear is mechanics and electricity. So it's a different combination, but the mechanics content is exactly the same. All right, so if you're doing linear, you should use all of the international A-level papers because there's more of them than there is with the linear papers. Linear is only examined in the summer, whereas modular have sittings in summer, October and January, so 3 times the number of papers. Okay, so I went through all the questions, multiple choice, all the way up to question 12, I think. So this is the multiple choice answers, and you can find it in the same playlist. And if you haven't watched it, you may want to go and watch them first. So these are the 10 multiple choice. International A-level papers have 10 multiple choice questions, and the linear have 8. That's basically the difference in the introduction. And then they both go into short structured questions. I went through this question in part 1, and so you can go and look at it. So if you haven't gone to see it, go and have a look, like it, share it with your friends, and then come back and watch this one. Question 13 is where I want to start. So that's question 12, we did that. Question 13 is also, I couldn't put all of my mechanics questions in the first video because I was using a sample of them as a practice exam. So here you have an escape lane, yeah? And it helps cars or trucks whose brakes have failed, yeah, when driving in it, it will slow them down. So you can see they put them at the side of the road. The photograph shows an escape lane, and the escape lane is basically made of sand, yeah, and it's horizontal, and you can see the road is going downhill. So if you go on the horizontal bit, obviously the gravity will not be pulling you down anymore, and if your brakes aren't working, that's a good thing. And then the resistive force, yeah, due to the sand on the vehicle reduces the kinetic energy of the vehicle. Okay, now this is actually called the work energy theorem. So work done by friction equals energy lost in kinetic energy. So work done will be equal to loss of kinetic energy of the car. That is basically what happens when you put your brakes on, except the work done is by the brakes, and this time it's going to be the resistance due to the sand. So as the truck enters the horizontal escape lane with the kinetic energy given here as 8 megajoules, or 8.0 times 10 to the 6, it says the sand exerts an average resistive force, so you can use this as the value that you need to work out to put in the work done, of 3.5 times 10 to the 5 newtons on the truck as the truck comes to rest. So the final kinetic energy is 0. So all you need to know is the loss of kinetic energy will be this much. Okay, so the loss of kinetic energy is then known, and you got to work out the work done using this force, and work done by the resistive force is this average resistive force times the distance it takes to stop. So you got to talk about you got to calculate the distance moved, yeah, by the truck on the escape lane. It will stop moving when it comes to rest. Okay, so F times S will be equal to loss of kinetic energy, change in kinetic energy. Okay, so we know the change in kinetic energy and we know the force. All we've got to do is to plug them in. 8.0 times 10 to the 6 divided by the resistive force which is 3.5 times 10 to the 5. So it'll be basically 80 divided by 3.5, and I've already done the calculations to save time. 22.9 meters to 3 significant figures, and you can round that up. That's meant to say 3 significant figures. You can round it up to 2 significant figures in the answer. Okay, so approximately 23 meters, 2 sig fig. Okay, because the data provided is only given to 2 significant figures. Part B, the resistive force exerted by the sand on the vehicle is proportional, yeah, so the resistive force is proportional to the weight of the vehicle. And the weight of a car is less than the weight of a truck. So they want you to figure out, explain how, the deceleration of a car would compare with the deceleration of the truck. Yeah? Well, in fact, it's going to make no difference, because although you have more weight, you will then have, it follows that you'll get more resistive force, but you also have the same increase, you also have more mass. Okay? So although you have more weight and therefore more resistive force, you have more mass. So the deceleration will be equal to the resistive force divided by the mass. Okay? Now the resistive force is proportional to the weight, so you could just change this to proportional too, because we're not doing any numerical. The resistive force is proportional to the weight, so you could put weight divided by mass, and since weight is equal to mg divided by m, you can see that the mass just cancels out. So the mass is not going to make a difference. Mass, weight, yeah. The acceleration is independent, yeah. Acceleration is independent. That's what I'm trying to write, independent. Let me write it again. The acceleration is independent of mass or weight, because they both cancel each other out. They factor in twice in the Newton's second law analysis. Remember, that's just basically Newton's second law. If you increase the weight, you increase the resistive force, but you also increase the mass that you got to change by the same proportion. Okay? So deceleration, here you go to say, therefore deceleration for the car and the truck will be the same. Okay? Obviously, when you're writing it, you do it in your own way. I'm just explaining it to you. Here's the mark scheme for both parts. I'll let you stop the video. You can analyze it yourself. I'm going to go straight into question 14 because I'm on a time deadline. Okay, so an air track. We did this one, air track. This we did in the original run through. So I did some of the mechanics ones already. Yeah. And question 15, I didn't do. Yes, it's blank. Okay, so here you got a hydroelectric power station inside a mountain, and it says that the water flows through a pipe, to a generator, and the pipe has a length of 350 meters, and it's at an angle of 55 degrees, so it doesn't go straight down. So first thing you can do, because obviously the potential energy that you want, the change in height is equal to 350, which is the length, times the sine of the angle. 350 sine 55. And if you do that on the calculator, the loss of height in that position, and I'm going to draw it on the diagram, is 287 meters. So in other words, it goes from there to there in this right angle triangle, and the vertical component is 287 meters. So that's the change in height, and that's where the energy comes from. Okay? So it says the gravitational potential energy of the water used to generate electrical power. In 1 minute, that's 60 seconds, it transfers this much water volume, and the density of water is given as 1100. So that means it's a bit salty because water is 1000 pure water. So the mass would be equal to density times volume. Yeah, so all you've got to do is multiply those two together, 1100 by 1700, 1100 by 1700, and that gives you the mass in kilograms, which is 1.87 megakilograms. We don't often use megakilograms because kilograms already has a prefix, so we would normally use standard form. So that's your mass. There's 1 mark. Okay, so now we could work out the change in gravitational potential energy, yeah, that mass would have. So you put 1.87, gravitational potential energy being mgh. Delta H we worked out, 1.87 times 10 to the 6, times 9.81 for g, multiplied by the height that we worked out, which was 287 meters. And that gives us the energy in joules that the gravitational potential energy provides. 5.26 times 10 to the 9 joules if you put in your calculator. Yeah, and remember, that's energy transferred by the water. So it's transferred by the water, but they want us to work out the power transferred. So this is in 1 minute. That's how much you transfer in 1 minute. And if you want to get the power is the change in gravitational potential energy divided by the time it took. So you just basically divide that answer by 60, 5.26 gigawatts, or whatever, gigajoules, times 10 to the 9 is giga, divided by 60, and that gives you the power. 87.7 megawatts. Yeah? Which is approximately what they wanted us to show, 88 megawatts. So to 3 significant figures is 87.7, and to 2 significant figures it's 88 megawatts. So we have shown what they asked us to do. So show that means prove it mathematically. We have now done that. So we get 1 mark for working out the mass. 1 mark up here for working out the vertical fall, 287 meters. So you're using your ability to resolve at an angle. Okay, remember sine theta if it's the opposite angle. And then you get 1 mark for working out the gravitational potential energy. 3, 1 mark for working out the power, and 1 mark for showing that it's approximately 88 megawatts. The question has not finished. Water travels from the lake, it says, through 4 identical pipes. So if you've got 4 pipes, the total power, they're telling us that the total power wasted has been worked out to be 256 megawatts. So we want to calculate the efficiency. So the efficiency, yeah, is equal to the useful power out, which is power in minus power wasted. We worked out power in before, divided by the power in. And if you do the maths, you'll see the efficiency will be, the power wasted is that, but the power in is going to be equal to 4 times 87.7 megawatts. Let's keep it all in megawatts. So it's going to be 4 times 87.7 or whatever it was, is going to give us 350.8. That's the power in, minus the 256, which was, they said, wasted, also in megawatts. Divide that by the power in, which was 350.8, and that gives you an efficiency of 0.27 or 27%. Okay, you don't have to put it in percentage terms. So you get 1 mark for working out the efficiency and 1 mark for putting the numbers into the efficiency equation. 2 more marks, done. Here's the mark scheme, working out the density. So there's alternative methods they're showing you. I think the method I showed you was the best. And the total for question 15. Okay, question 16 is about moments. This is a balance which is balanced on this string point. Okay, so a balance is formed by a beam suspended from a string. A dish is hung. Here's the dish. On one side from the beam, a dish is hung from the beam, and the balance is used to measure a fixed portion of rice. So obviously the weight here, weight of rice and the dish, rice plus dish, R plus D, is balanced by the fact that they got the mass of the beam at the other end on the other side of the string. So you got the distances there to be able to work out the answer to the question. But first of all, they want you to show, that when the dish contains, it says 1 portion of rice, the equilibrium, you have equilibrium. So we're going to use this later on to balance the clockwise moments, which is due to the dish, with the anti-clockwise moments, which is due to the weight of the beam, which all the weight is on the left. But before they do that, they want you to state the conditions needed for an object to be in equilibrium. Okay, there are 2 conditions. First one, there must be resultant forces, all resultant forces, or the resultant force, that means all the forces added together, must be 0. They must add up to 0. Remember, they're vectors, okay, and they can come in any direction. And second of all, the resultant moments taken about any point, you should say. In this question, we're going to take it around the string, but you could take it about any point, and mathematically it would be the same. The resultant moments must also be 0. So there's 2 things that must be 0. For example, up and down forces must be balanced. All the forces in any 2 opposite directions must be balanced, but you can just say it like this. The resultant force must be 0. Just like the resultant moments taken about any point must be 0. There are 2 conditions for equilibrium. Something you need to make sure you got in your notes before Wednesday if you're one of my students. Okay, the next question, and this is where the maths comes in. It's a 6-mark question, mathematical question. The dish is moved along the beam, so the horizontal distance from the string changes from 25 to 7 centimeters. Now, if you go back to the question, just because we didn't talk about it, the question has it such that here you got 1 portion of rice. So 1 portion of rice is balanced at 25 centimeters. So if they move it inwards, it means they must be putting extra rice in the dish. Okay? So it says rice is added to the dish until the balance is in equilibrium. Yes, at 7 centimeters. Deduce how much rice there is in terms of portions in the dish. Okay? So, for example, they want you to deduce whether there are 3 portions now. Okay? Because it goes from 25 to 7. Yeah? So the distance is crucial in calculating the moments, and they've given us now the weight of the beam. So the weight of the beam was the counterweight to the rice. So the weight of the beam acts through the center of gravity. So the weight of the beam here is 3.1 newtons, 8 centimeters from the string. Okay, that's 3.1 newtons. Okay, so we know what we're balancing. 1 portion is balanced 8 to 25. Yeah, and we can work out the portion of rice, how much it weighs with the dish. Okay? And we then need to take into consideration that the dish has its own weight. Okay? So, initially we want to do it with the 25 centimeters. So first of all, do it initial situation with one portion. So with one portion, the sum of the clockwise moments due to the dish and the rice will be equal to the sum of the anti-clockwise moments. That's how I do it. About the string. S for string. About the string. Okay, that's what we're taking moments about. So let's just call it the weight of dish with rice. Weight of the doctor. Weight of the dish and the rice multiplied by the original distance, which is 0.25 meters, must be equal to the weight of the beam, which is 3.1 newtons, and the distance is 0.08 meters. So now we can work out the weight of the dish and the rice as the only unknown. By dividing both sides by 0.25, you'll get the answer of 0.992 newtons. Now remember, that's dish and rice. So now we know one portion of rice equals 0.992 minus the weight of the dish, which is given above, underlined in blue, of 0.64. So the weight of one portion of rice is needed, and you'll see that it's 0.352 newtons. Okay? So far, we have got ourselves 1 mark just for knowing how to take moments, 1 mark for balancing the moments, so doing the whole thing here, and then 1 mark for working out the weight of one portion of rice. Now, the second situation, with extra rice. Secondly, with extra rice, now we need to do it again. Again, the sum of clockwise moments equals the sum of the anti-clockwise moments. And this time, we know that the extra portions, yeah, so we're going to have x portions. And we're going to find out how many x is. So x equals question mark. All right, so I'm going to just try to write this out in the space with my big writing. So we have one portion of rice is 0.352. 0.352, that's the weight of one portion. And we got x number of those, so 0.352x, times the distance. This is the clockwise moment again. That's going to be plus the weight of the dish, which is 0.64 newtons. And both of these are now at 0.07. So they're closer to the string than the beam weight. Okay, and this must be equal to the original anti-clockwise moment, which was 3.1 times 0.08, which is equal to 0.2428. Okay, so we already knew that hasn't changed. The anti-clockwise moment is still 0.2428. So the only unknown is x. So we can divide both sides by 0.07. Yeah, so we can do that. Yeah, and then we can take away, we can then take away 0.64 from this side. So that what we're left with then is 0.352x equals whatever that is. And I've worked it out. So that equals, so therefore x will be whatever that equals, which is 2.903. I'm just trying to keep it accurate in case I lose a mark for being too far from the final answer. Divided by the one portion, 0.352, and that tells you that you're about 8.25. X equals 8.25. So no, not 3 portions. For that balance, it's 8.25 portions. So we got 3 marks. Now 3 more marks, presumably the 3 more marks are given for stating that the clockwise moment with 3 portions is equal to the anti-clockwise moments. So basically this bit of the maths, and then to work out 8.25, and then for this conclusion. Okay? You'll see the mark scheme on the next slide. Okay, I think you can see it all. I'll let you pause should you need to. Once again, if you find my videos useful, I would expect you to support my hard work by liking each video you watch. I notice there's someone who likes it straight away and then everyone else watches it without a thank you or a like. Okay, so let's get into the attitude of gratitude. Okay, if you could please, that will be great. We got over 1,250 subscribers by the end of the day, I reckon. So a tugboat is a small boat, yeah, that is used to pull large ships, and they use a thick rope. So this is a materials question. The sample of rope is tested to make sure it will not break when it's pulling a ship. The original length is 36.8, and they want you to calculate the strain when the length has increased to 38.1. So strain is given by epsilon, which is change in length over the original length. So it will be 38.1 minus 36.8 divided by 38.1. And that gives you a strain of 0.0353 to 3 significant figures, yeah, which you should probably go approximately 0.035. 2 significant figures is sufficient, yeah, in my opinion. Okay, although they have given you 3 significant figures in the data here. Then they've shown you the stress strain graph for the rope. You can see it's kind of elasticy because it's not a straight line relationship. Okay, now they're going to ask us, because I remember when I did this question, they're going to ask us what, at this point of strain, what is the stress? So you've got to go up there, it's here, so that's the strain, which I think is 110. So we're going to use 110 megapascals in the next part of the question. Draw the line up and show how you got it. So the next question is asking us that the diameter of the sample is given us in millimeters. So you've got to change that into area in meters squared. So that will be pi d squared over 4. And that would be give you, so that would be pi times, I don't know why I'm doing it in yellow, pi times 220 times 10 to the minus 3 squared, divide that by 4, and you'll get the area to be equal to 0.0380. I've ignored the last significant figures. So once you got the area, you'll get 1 mark. So why do we need the area? Because they want us to use that 110 megapascal to determine the force. Okay, so that you use the strain to go to the graph, find the megapascals in stress, and then you know, since stress equals force over area, it follows that force equals stress times area, 110 times 10 to the 6 times the area, 0.038 meters squared, will give you the strain, the force that's applied to create that effect. And it gives you 4.18 times 10 to the 6 newtons. And you could put it to 4.2 times 10 to the 6 newtons. Don't forget your units, 2 significant figures, or you can leave it as 3 significant figures. Okay, I think 2 significant figures is better in this case. And then it says, explain how the area under the graph, so the area under the graph, you can, and the volume of the sample can be used to determine the energy stored. Okay, now the area under the graph is stress times strain, which is equal to force over area times extension over original length. Now you can see that the top of that is equal to, the top is force times extension, so that's work done, stretching something, and the bottom is A times L, which is volume, so that's work done divided by volume. Okay, so the area under the graph is joules per meter cubed. So if you multiply the area that you calculate under the graph by the volume of the sample, you'll get the strain energy stored, the strain energy. Yeah, which is, you could say, the elastic potential energy. Stored in that volume. Okay? I hope that makes sense. So you'll get 1 mark for doing that, 1 mark for showing us work done on volume, and 1 mark for saying that is multiplied by the volume will give you the energy rather than energy per meter cubed. Okay? All right, so the mark scheme, part A, part B. I'll let you stop the video if you need to. And there you have the alternative communication skills required to do that. Question 18 we did in the first run through. So you go back and have a look at that video. It's in the same playlist. Everything is organized in the home page as playlists. So if you're looking for a particular exam or a particular year, go and look there first and you will find it. So you go to the home page of the channel, and it's logically ordered. Okay. Question 19 we did as well. Question 19 was that projectile question. Yeah. That's in the first part of this paper run through. So we are left with only 1 question, and I need to be quick. Yeah. So the final question, a student determined the terminal velocity of a metal sphere falling through a container of oil. So this is a core practical. Yeah. Student released the sphere and explain why the sphere reached terminal velocity. So they want you to say, initially all you got is weight, so there's a resultant force, therefore there's an acceleration. I need to go fast. I have an appointment in 14 minutes time. Okay, so the sphere accelerates, so resultant force is only due to the weight, there's no drag. And then as it speeds up, as it speeds up, you then get force due to drag, which is 6 pi r eta v. So the drag increases, and at one point, eventually, the weight, which doesn't change, will be equal to the drag. You get equilibrium, and you reach constant speed. And that constant speed is called terminal velocity. Okay? So you get 1 mark for saying that there's just a resultant force downwards due to weight. That causes acceleration, then it speeds up, and eventually you get balance forces. Okay, next bit, they want you to do some calculations. So it says it's falling through 0.45 meters in a time of 7.3 seconds. So if you put those two together, you can work out the terminal speed. Yeah? So the terminal velocity will be 0.45 divided by 7.3 seconds, and that gives you a terminal speed of 0.0616. I'm going to change the color. 0.616 meters per second. So you got the speed, that's 1 mark. 3 marks we want, and then they want you to work out the drag force. So they want you to know Stokes' law, find it in the equations, 6 pi eta RV. They've given you eta, they've given you R, so you've got to put those numbers in. I'm going to have to cut this short, put the numbers in. If you put all the numbers in correctly, including the velocity, so velocity goes in there, this goes in there, and this goes in there, times 6 pi, I'm sure you can do that. You will get an answer of 2.19 times 10 to the minus 4 newtons. If you can't get that, have a look at the mark scheme as I need to get ready. Okay, the next question. It says the student repeated the experiment using a second sphere with a greater diameter. Okay, so it's not simple, this one. It's the last part of the exam. The density of the second sphere is the same. So it's the same material, no change there. And the temperature and the conditions remain the same. So exactly the same. The only change is diameter. Explain how the time taken for the ball to fall through the 0.45 meters, compares with the original sphere. Okay, so say you've got the sphere. So although drag force, the drag force is proportional to the radius, which is the diameter, that's not the most crucial factor. The weight is proportional to r cubed, because weight is proportional to volume, and the volume of the sphere is 4/3 pi r cubed. Okay. Now, since the weight has a bigger, the radius has a bigger effect on the drag force, it will actually take longer. It will take longer to be able to. The sphere will need to attain a higher speed. It will take longer to reach terminal velocity. But the terminal velocity, because it's got to equal the bigger weight, the terminal velocity, once it does that, which is what we're talking about, will be greater. And if the terminal velocity is greater, then since Vt equals the distance, which is 0.45 over the time, if the velocity is greater, the time must be smaller. So the time to fall, we're going faster, time will be less. Okay? That's basically the logic behind it, but it's actually more complicated than that, because there's also upthrust which will increase. So I think this is quite a complicated question. So you get 1 for explaining that you know that the drag force is proportional to the radius, and that is proportional to that. And then some kind of explanation will get you the 3rd mark. Remember, that's the last mark in a 80 mark exam. So they're going to try to confuse some students, and it's okay not to get that final mark if you don't get it. Okay, well, thanks for watching. I hope you found that useful. It's a quick run through. Normally I handwrite them before, because my handwriting is better than my Apple Pen writing. And make sure you use it before if you're linear, make sure you use it before Wednesday's exam to improve your technique and to understand the concepts better. And make sure you give it a like. Okay, don't watch videos without showing your appreciation. There's a lot of time that goes into making these videos. Anyway, thanks for watching. Catch you next video. Bye for now.